In this video, we're looking at the motion of charges and dipoles when they are in an electric field. First, we need to look at a parallel plate capacitor, which produces a special type of field. A parallel plate capacitor is made of two parallel conductive plates, and they are generally characterized by their plate separation and by the area of the plates. The plates will store equal and opposite amounts of electric charge. To find the electric field of a parallel plate capacitor, we will use our result from the infinite plane of charge. This is a valid approximation assuming the plates are close together and we're looking at the field near the plates. If you remember, the electric field from an infinite plane of charge did not depend on distance. It was the same regardless of how far away we looked from the plane itself. Since the field does not depend on distance, and each plate will have the same amount of charge, the field strength for both plates is equal at every point in and out of the capacitor. The only difference is the direction. On the left side of the capacitor that I have drawn, the field from the positive plate is away to the left, and the field from the negative plate is to the right. So the field cancels since it's the same strength. This is also true for the right side of the capacitor. Inside the capacitor, the field directions will be the same, so instead of canceling, they will add. Not only that, but again, the field strength is constant everywhere. So we call this a uniform electric field. We draw this uniform electric field with parallel electric field lines that are evenly spaced apart. To get the electric field inside, we can double the electric field result we got from an infinite plane, and we get the electric field inside the capacitor is the charge on either plate divided by epsilon naught times the area. And in this result, we have written the charge per area instead of surface charge density. Outside of the capacitor, there is no field, but remember this is just an approximation. In reality, the plates are not infinite, so there is some dependence on distance. This means the fields won't perfectly cancel on the outside, and there will be some bending in the field lines at the ends of the plates, since they're not infinite. This non-zero field outside that actually exists, we call a fringe field. For now, our approximation is good enough, and we want to consider the motion of a charge inside a uniform electric field like we've created here. The electric field will exert a force equal to the magnitude of the charge times the field strength. And if this is the only force or net force felt by a charge, we can use Newton's second law to solve for the acceleration. Doing this and substituting the force from our electric field, we find the acceleration of our charge is equal to the charge divided by the mass all times the electric field value. We call the charge divided by the mass the charge to mass ratio. And if we know this ratio and the field strength, we don't actually have to know the specific mass or specific charge to find the acceleration. Since the charge, mass, and electric field strength here are all constant in this case, the acceleration of our charge will also be constant. And constant acceleration means we can use our kinematic equations to describe the motion of the charge. I'll rotate the parallel plate capacitor, and now the field will point downward. This means that the acceleration of a positive charge will also be downward. And a constant downward acceleration should remind you of motion that we have looked at before for masses near the surface of Earth, where gravity is constant. We can treat a positive charge that is launched perpendicularly to the positive plate as though it's in free fall. It will slow down as it moves closer to the positive plate and eventually stop before speeding up toward the negative plate, just like if you throw a ball straight up into the air. If we launched the positive charge at an angle, now we can treat it like it's in projectile motion. In both of these cases, instead of using gravitational acceleration, we would find the acceleration using the charge to mass ratio and the electric field strength. Let's look at another case of a charge moving in a uniform electric field. But now we'll fire the charge very quickly and perpendicular to the electric field lines. The charge will be deflected toward the negative plate as it would before, but if the charge is moving fast enough, it will escape the electric field and leave the capacitor at an angle. Because the uniform field is perpendicular to the initial direction of motion, this component of velocity will remain constant. So in the example I've drawn, the charge begins with only an x component of velocity. Since there is no acceleration from the field in this direction, it remains constant just like in projectile motion. In order to find the deflection angle due to the field, all we need to find is the y component when the charge leaves. We can do this using kinematic equations if we're given the appropriate information and properties of the capacitor. Then we just plug into inverse tangent using our original x component and new y component of velocity. Now let's look at an electric dipole placed in a uniform electric field. Assuming the dipole begins in some arbitrary orientation relative to the field, so it's just pointing at some angle, and it is not aligned with the field, each pole of charge will feel a force. And since the poles have opposite but equal charge, they will feel an equal force in opposite directions. These forces will cancel, so the net force on the dipole is zero. This means it won't translate, but the forces will cause a torque in the same direction. And in the case that I've drawn, the torque will be clockwise. This torque will cause the dipole to rotate until the dipole is aligned with the field. When we have two equal and opposite forces that are parallel like this and act such to rotate the object, we call this a couple. Now let's find the magnitude of this torque on the dipole. We can write the torque as the force times the moment arm, or perpendicular distance from the force to the axis of rotation. The dipole will rotate about its center, and the distance between the poles we'll call S, as we did in a previous video. This means the perpendicular distance from one of the forces to the center of the dipole is half of S times sine of theta, since the perpendicular distance is the opposite side of this right triangle. The force on each pole is equal to the charge times the electric field strength. And since the torques are equal, we'll just double the torque on one charge. This gives us 2 times the moment arm D times the force. Plugging in our 2 and 1/2 will cancel, and the rest of the quantities are multiplied. We've already seen this quantity Q times S, and it is the dipole moment P. So we can write the torque in terms of the dipole moment. This gives the torque equal to the dipole moment times the electric field strength that it's placed in, times sine of the angle the dipole makes with the electric field. Also notice this looks like the magnitude of the cross product between two vectors. The dipole moment and electric field are indeed vectors, so we can express the torque as the cross product between the two. Here, the torque is maximum when the dipole is perpendicular to the field, and it is zero when aligned with the field. Finally, let's look at a dipole in a non-uniform field, such as the one produced by a point charge or a sphere of charge. Here we know the positive pole will be pushed away and the negative pole will be pulled toward our positive point charge. However, the field of a point charge falls off the further away you are. This means the positive pole on the far side feels a slightly weaker force than the negative pole, which is closer. This leads to a net force on the dipole that is toward the point charge. In general, each pole of the dipole will feel a different amount of force in a non-uniform field, and this will lead to the dipole moving closer to where the field is strongest. Hopefully you saw how the motion of charges and dipoles in electric fields looks similar to motion that we've seen before, specifically in Physics 1. If you need to brush up on forces or rotational motion, I would highly recommend going back to the basics from Physics 1. And that's it for this video. I'll see you in the next one.